right, so people in the back, is this still too quiet or? No, all right. So go ahead and get started. I'm going to give you a plan for what we're going to do today. So I'm going to start with something that's actually not going to be on the test. I'm going to start with a brief overview of logic. And even though logic itself is not it's not in scope on the prelim, I think it will tie together everything else that we do well, and it will give you the intuition and the reason why we do certain, like why we write proofs the way we do. And it will give you the reasons behind why we write our proofs the way we do, and how you will know when you see a problem how to write the proofs in a way that is rigorous. And so the first maybe like 20 minutes is not actually going to be content proper for the prelim, but I think it's the base material is going to be a foundation for what we're going for the rest of the content of the prelim that we're going to go over in the rest of the session. And I'm going to do a mixture of some content review and some of the problems. I'm not going to go over all of the problems, but I'm going to go over a representative sample of them that will give you good examples for certain things that you want to look out for, and certain things that you want to be careful for. So go ahead and start. So in math, we are primarily concerned with the notion of truth and falsehood. And we use proofs to show that things are true. Show that statements are true. And we use counterexamples to show that statements are false. Is the chalkboard writing big enough for the people in the back? Are you guys able to see? Okay, so that's okay. So I have to write bigger. All right, I'll make sure to write bigger then. And so when we're talking about truth and falsehood, we need to have a language by which we talk about statements and whether these statements are true and false. And so in math, we call a statement which is true or false a proposition. Is this good or? In math, we have statements called propositions. Is this good? All right. Propositions, which are statements that are true or false. And so, for example, we can have a statement that's like, it is raining outside. I believe that statement is false. Or you can say, right now the time is 6:43, and that statement would be true. And so in math, propositions are statements that are true or false, and we can use variables to represent propositions. For instance, in algebra, we might have variables like x and y to denote numbers. In math, when we're talking about propositions, we may also use variables to represent propositions. And so here I'm going to write out a chart. Here I'm going to write out a chart that there's algebra and logic. And so we can have things that are variables. In algebra, we might have x, y representing numbers. So we are representing numbers. In logic, we may have variables like p and q, represent statements that are true or false. Is the board writing okay? Or so just as in algebra we might have variables like x and y which represent numbers, in logic we can also use variables like p and q or any other letter to represent statements that are true or false. And one thing is that the fact that I use lowercase and uppercase or what letters I use is actually not too important. The fact is that in both areas of math we can use variables to represent certain objects in that system. In algebra, we use variables to represent numbers, and in logic, we use variables to represent statements which are true and false. When we're using variables like x and y in algebra, we can use operations that will allow us to create more complex expressions. For example, we can have things like plus, we can have things like times, minus, divide, etc. And similarly, we will also have the same in logic. And these operations operate on logical objects, which are propositions. They do not act upon numbers. And similarly, these operations, plus, times, minus, and divide, operate on numbers or numerical variables and do not operate on Boolean variables here, p and q, which represent statements which are true or false. It's important to see that there's a distinction here that these represent numbers. These represent Boolean values. Boolean values that are equal to whether or not that statement is true or false. Therefore, if p is something like it is raining outside, the value of p is false. So what kind of operations do we have here? I'm going to here draw a table. See p and q. We can have operations p and q. Or this is a symbol, but I'll write p and q, p or q. Not p. P implies q, and p if and only if q. So this is like implies. This is if and only if. And the way we define these operations is by enumerating all possibilities of what p and q can be and what the value of the operation is. So in other words, this is analogous to saying, if I want to tell you what plus is, I can make a table of every combination of like x is 0, y is 0, x plus y is 0. X is 1, y is 1, x plus y is 2. And so we don't usually do that because there are an infinite number of possibilities here, x and y, that we would have to enumerate. And so normally when we define plus, we don't define it in this table. But here when we're defining logical operations, since p and q represent true and false values, we can enumerate completely every possibility. And the definition of each of these operations follows by what the truth value is here, 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 and here. So if p is true and q is true, p and q is true. This is false, false, false. P or q, true, 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 false. Not p, this is false, false, true, true. And all of these operations, I hope, are compatible with your own intuition, which is that if we want p and q to be true, that is only satisfied when p is true and q is true. When one of them are false, then p and q is false. For example, I can say something like at the dining hall there are cookies and brownies, so the dining hall is cookies and the dining hall is brownies. And even if one of those things are false, that entire statement that I said involving the and is also false. And so I hope these truth values here are compatible with your intuition, that if we say p and q are true, it will require both of them to be true. If we say p or q to be true, that means at least one of them needs to be true. And if not p is true, when p is true, not p is false, and the other way around. Here we have two other operations, P implies Q, which is saying if P, then Q. And if I give an example that says if it is snowing, then class is canceled. What is the truth value of that statement when it is snowing and class is canceled? That the value of that if statement is true. So if someone told you if it's snowing, then class will be canceled. Let's say it is snowing, class is canceled, then you are telling the truth. If it is snowing but class isn't canceled, then you are lying. Therefore, this if statement is false. But if it's not snowing and class is still canceled, you're not lying. You're still telling the truth. It's just not snowing. So your statement therefore has no applicability. And so you're still telling the truth. It's just that your statement sort of just doesn't apply. And so in logic, we will define false implies true to be true, and similarly, false implies false to be true as well. In these two cases, it's like, are you telling the truth when you say if it's snowing, then class is canceled? Let's say it's not snowing. It doesn't really matter what happens. You're still telling the truth. You haven't broken your promise. You haven't lied by saying that if it's snowing, class is canceled. It's just not snowing. We just don't know what's going to happen. But here, if and only if you say if it's snowing, if and only if class is canceled, it means that if it's snowing, that means class will be canceled. And if class is canceled, it has to be snowing. In other words, the only time when it's snowing is matching when class is canceled. The only time when class is canceled matches when it's snowing. And so if you make that statement, if it's snowing, then class is canceled. If both of those things happen to be true, you're still telling the truth. If it's snowing, the class isn't canceled, then you're lying. It's false. If class isn't canceled, if it's not snowing but class is canceled, you're still lying in this case. If it's not snowing and class is canceled, you're still lying because you said it's snowing if and only if class is canceled, which means class is canceled only when it's snowing, and it's snowing only when class is canceled. So even if one of those things weren't to happen, if one thing were to happen and the other was not to happen, we'd still be lying. But if both of them didn't happen, we would still be telling the truth. Are there any questions about the definition in this table? Can I have like thumbs up or medium as to but I want to call your attention to a few things inside this table which are noteworthy. One is particularly in the truth table of P implies Q. Most of the mathematical statements you encounter in this class are of the form if P, then Q. If something, then something. To prove if P, then Q, we only need to worry about this case here. We only need to worry about that when P is true, that Q is also true. Because if P is false, we don't really have to worry about that. We know that if statement is true. We only need to worry about when P is true, that Q will also come out true. To provide a counterexample for P implies Q, you have to get yourself into this row. You have to find something where P is true and Q is false. And so to talk about more about this table, I'm going to move this one up. Talk more about this table. I'm going to now give you another table, which is in which I'm going to specify here if we want to prove, use, or counterexamples. And let's say we have an and statement or implies if and only. What happens when you have these statements and you want to write proofs involving statements that have and, or, implies, or if and only if? And to remind you, in a proof, a proof always starts. So proofs always start with something you know, and end with what you want to show. In other words, when you're writing a proof, you will always start here with something like assume something, and then you go down and you get to the conclusion. And as you are progressing through the proof, as you're moving through the proof, the statements here, as you're moving through the proof, the statements here are the statements that you know, and the statement down here is the statement that you want to show. This is the stuff you already know, and by logical deduction and reasoning, you keep generating newer and newer statements until you reach the point you get to the statement you want to show. So in other words, a proof should be sort of like an explanation or a story in which you start with something that you know, and you tell the story about how to get to the place where you get to the thing that you want to show. Just like in a book, you might start out with certain characters and events that you know about, and as the book progresses, these events begin to snowball and get to a conclusion. Similarly, in a proof, you start with what you know and you get to what you want to show. Now, the thing about a proof is that you actually know where you're going to end up, and you need to fill in everything that's in between. And so we have statements up there that are like ands and or statements or implies. I want to fill in this chart to show you what you can do with these statements. So in this row, we're going to say, what happens if you want to prove a statement that involves and? Here, we're going to say, what happens if you already know a statement that involves and? What can you do with it? And here, if you want to show a counterexample to an and statement, what do you do? And so prove is, what if this is like you already know. This uses if you want to show. So let's say we have an and statement. Let's say you have an and statement you want to show. Let's say you have an and statement and you want to, this is backwards. If you want to prove, you want to show, you want to use, this is something that you know. Let's say we're talking about an and statement like P and Q, or let's say it's raining and it's cloudy, like an and statement. If you want to show an and statement, if you want to prove something that's and, you will need to, so maybe I can write P and Q, P or Q, P implies Q, P if and only if Q. If you want to prove it, you need to prove P and prove Q. So you need to, so when you have to prove an and statement, you now essentially need to prove two things. You need to prove P individually, and you need to prove Q individually. P or Q, if you want to show P or Q, you only need to actually show that one of them is true. So here, it's like, you just need to show that, so it's enough to show one of P or Q. This isn't always necessarily a foolproof method. In fact, none of these things are like hard and fast rules, but there are guidelines for you to think about how to go through proofs. In this case, if you want to prove a statement of the form, let's say it's raining or it's cloudy, it's enough to just show that it's raining. That's the whole. Then the whole statement is true, and it's enough to show that it's enough to also show maybe that it's cloudy. Therefore, it's raining or it's cloudy. To show P implies Q, we want to assume P and then get to Q. And to prove P if and only if Q, you want to prove both P implies Q and Q implies P. And have thumbs up and thumbs down as to how you're doing this. In this row, we were talking about what happens if, so in this row, we were talking about what happens if you want to end up here, and the thing you want to end up is, let's say, an AND statement. Or the thing you want to end up with is an OR statement. In this row, the use row, this is saying what happens if you already know something that's an AND statement, or know something that's an OR statement. And if you already know that P and Q is true, that means you already know P and you know Q. If you only know P or Q is true, then this is probably a proof by cases. The cases will be a little more space here. So case 1 is P, case 2 is Q. So in other words, in this, if you only know P or Q is true, you probably want to use a proof by cases saying, in the case where P is true, what do I know? In the case where Q is true, what do I know? In this P or Q section, you don't actually know. You can't conclude P is true, nor can you conclude that Q is true, because you only know that at least one of these two is true. You don't know which one is true. So you can't just say, oh, I know P or Q, therefore P. I know Q is true, therefore Q. You have to split it up into a crossroads in which you say, what if P were true? What do I know? What if Q were true? What do I know? And hopefully in both of those crossroads, you end up getting to the conclusion. To use P implies Q. So if you know P and you know Q, in other words, if you know this if statement is true and you know that P is true, then you automatically guarantee Q is true. That should be clear from the table. If you know P implies Q is true and you know P is true, you have to be in the top row where Q is also true. And here, P if and only if Q, if you know P, then you know Q, and vice versa. So you can also, you can know P and you can get to Q, or you can know Q and get to P. If you look at this column up here, if you know P, if and only if Q is true, if you know P, that guarantees that the Q is true. And if you know Q is true, that guarantees your P is true. The last thing is for a counterexample. To show P and Q is false, all you need to do is show one of them is false. So you just need to show one of P or Q false. To show the OR statement to be false, you need both of them to be false. So you need to show both false. To show P implies Q to be false, you need to show you need to get it, maybe not show. To provide a counterexample, you just need to provide one example in which P or Q is false for this. And here, you just need to provide an example where both are false, or here, or P implies Q. To get P implies Q to be false, you need to show the example where P is true, Q is false. And to show P if and only if Q is false, you need to get an example where you end up in one of these false categories. So you have to get an example where P true, Q false, or P false, Q true. So here, this is in this counterexample row, we're saying in order to prove a statement of this form false, you need to give an example that satisfies this. To show P and Q is false, you give an example that one of them is false. To show P or Q is false, you give an example that both of them are false. To show P implies Q, so to show if P then Q, if P then Q is false, you need to give an example where P is true, Q is false. And to show that P if and only if Q is false, you want to give an example where P true, Q false, or alternatively, you can give an example where P is false, Q is true. Note that in this case, because of the use of the word or, you need not give two examples, you need to give one example, either this or this. I'm going to, so can I have thumbs up, thumbs down as to where we are on this? I want to put this board here. This here. I also want to introduce you to two other types of statements besides these, and that is the statement of for all, symbol for all, and there exists. I believe these symbols will be covered on Monday, but for all, if I write a statement like for all n p of n, what this says is implicitly here, when I say for all n, there's some set of things, some collection of things which I'm talking about. So if I say like for all like Cornell students, you have a net ID. Properties that you have a net ID, and the inherent implicit set that we're talking about is that is Cornell students. Here, if I say there exists n p of n, it's saying there is some n satisfying the property p of n. And so to talk about this, I want to add maybe two columns to that table, which are talking about for all and there exists. That something that to show for all n p of n, to show that every n has this property p of n, you want to take an arbitrary x and show p of x is true. The intuition behind this is you're saying every n satisfies the property p of n. And how do you prove that? How do you prove that every n satisfies the property p of n? Is you challenge the reader of the proof and say, take an arbitrary x. In other words, give me whatever you want, I will call it x, and I will show you that the thing you give me satisfies the property p. If you are confident enough to tell the reader, give me whatever you want, I'll call it x and show that that x satisfies the property p. That means you are confident enough to say that every n satisfies p of n. You're telling the reader, give me whatever you want, and I'll show you that it satisfies the desired property. That means that you must be confident that every n satisfies that property. Otherwise, you wouldn't let the reader pick whatever they want. To prove there exists, you want to give an example. Give an example. Let's say X, and show X satisfies P. In other words, to show that there exists this n where P of n is true. Let's say there is a Cornell student whose student ID ends with a 6. In order to show that there exists that Cornell student whose student ID ends with a 6, all I need to do is give an example. Let's say I find some student whose student ID ends with a 6, and I ask them to show me their ID, and it ends in a 6. Therefore, there exists such a student. To use the fact that every n satisfies P of n, it's whenever you have some n, you automatically know P of n is true. In other words, if you know that every n satisfies this property, whenever you're dealing with an n, you automatically know that it also satisfies this property. Here, to use that there exists, it's kind of tricky, but I might, one way I could say is, to use that there exists something, you might say, you can say, call X the object that satisfies P. What this does is, if you know there exists something that satisfies P, you can say if I know there exists a student whose student ID ends with a 6, I can say call X the student whose student ID ends with a 6 and progress from there using X. To show a counterexample of for all, if there's something that says for all, every element n has to satisfy this property. To show a counterexample of that, all you have to do is give an example where P of n is false. In other words, if I say for every student satisfies some property, to prove me wrong, all you have to do is to show me one student that doesn't have that property. Here, if I only say there exists some student with this property, to prove me wrong, you have to show every n does not satisfy P. This table here generally gives a pretty good guideline for how you can approach most proofs in this class. This table here gives you more or less a general guideline for how you can approach proofs in this class. They're not necessarily rules. There's still a bit of an art in knowing when to strategically apply the right rule at the right time. However, this will more or less give you a systematic process by which you can get yourself through a proof and be able to write papers. I want to now transition to the other type of proof that you have encountered in this class. First of all, we have thumbs up, thumbs down about this stuff here. Yeah.
I have a question. So, say you're trying to get to a conclusion, right? How do you know when you're using too much of the thing that you're trying to prove on your way to proving it? It seems kind of like a blurry line to me, and I don't know if there's any set rules saying you're making too much of a jump, saying that you're using something that you're trying to show in order to show the conclusion.
I think there's no good I don't have any good answer to that other than you'll probably be able to better tell when this happens more and more through experience.
Okay.
So I now want to now I want to transition to talking about the other proof technique that you've encountered in this class, which is the method of induction. And just a brief summary, induction what you always have is you have a proposition P of n for all n, usually like naturals or something like that. So whenever you see a proof that says something like prove for every natural number something is true, that is a good indication you want to use induction. Whenever you see, and especially when you see definitions which are recursive in nature, if you see something is relying on something before it, or you like, if you see like 5 is relying on how to deal with 4 and 3, or you see something that's like prove something for all naturals, this is a good indication you want to attempt a proof by induction. A proof by induction, it would be a good idea to write out your inductive statement P of n. What I mean by P of n, P here is what we talked about. It's a proposition, and this is a proposition that applies to n. Be careful that P of n, you don't think about this as like some algebraic function like P of n is n squared or P of n equals to like 5 or anything like that. P here is a proposition. That proposition applies to a specific value n. And this is why it's very important that when you are dealing with something like P of n, you do not write, so these are, do not write something like P of n equals 5, or P of n equals like 1 plus n squared. All of these things are have no meaning, because P itself is a proposition. P is a proposition, which means that it takes on values true and false. P of n is the proposition applied to the value n. That proposition, but P of n is still itself a proposition. When P of n is a proposition, it cannot equal to 5. P of n only represents true and false values. Similarly, I can't do something like this. Notice here, this is an algebraic expression. It inherently is like variables. These are using algebra variables. This P here is a proposition. And so you cannot set propositions equal to like algebra stuff. In a proof by induction, you always start with a base case. Let me just call it P of K0. K0 being the smallest case we need to consider. So in other words, if you're going to show P of n for n greater than or equal to 10, you want your base case to be 10. This K0 is like the smallest value of n that you need to consider, and you need to have an inductive step in which you prove P of n, or let's use a different letter. P of k implies P of k plus 1. Here, notice we are proving an if statement. We're assuming that if this proposition is true for a specific value k, then I can guarantee that this proposition is true for a specific value k plus 1. And notice here, if you're looking at this, you should know how to, this table indicates to you how to start up your proof. To prove this if statement, you're in this case. To prove it, you assume the thing here, and you want to get here. When you have P of k implies P of k plus 1. To prove it, you assume P of k to get to P of k plus 1.
Yeah, I had a question. What does it mean to like quantify n?
Oh, okay. So when you're giving, so that's a good question about quantifying n. what it means to quantify n is when you write out your P of n statement. Remember, P of n is a proposition applied to a specific value n. So what you don't want to do is write the statement P of n is something 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 for all n. Maybe here the goal is to prove that P of n is true for every n. But the specific statement P of n is the specific statement P applied to the specific value n. So you don't want to say P of n is something 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 for all n. P of n means apply the proposition P to the specific value n, not apply proposition P to every value of n. And I think I could probably answer this question better by giving you an example. So I'm going to do two examples here. I'm going to do two examples from the practice questions. I'm going to start with question question 3, and then if we have time, go to question 4. And so if I look at question 3, here to show that for all n greater than or equal to 1, that this sum here, so we're trying to show is for all n 1 plus the half third plus 1 over n. Here, I didn't totally write it out clearly, but this is like for all n naturals, n greater than 1. Notice here we have that case that we were talking about. We want to prove something is true for all n, which is naturals, and n greater than or equal to 1. To do this, I use this problem to show you a technique which may come in handy when you do your induction proofs. But here, to show this, we first need to use a base case. Since that base case, since we need to show that this is true for all the n's bigger than 1, the base case is when n equals 1. And to show this is true, we just say, right, what's this left-hand side? So left-hand side is just 1. Right-hand side, 1/2. Natural log of 1. The natural log of 1 is 0. 1 is greater than or equal to 0. But this gives you the base case. I'm sorry. So even before the base case, one good idea is to write out that statement proposition P of n. What P of n here is, P of n is the statement 1 plus 1/2 plus 1/3 plus 1 over n is greater than or equal to 1/2 natural log. P of n is not the statement this is true for all n. This is not P of n. P of n is saying this is the proposition I'm talking about, and I'm applying it to the value n. Therefore, P of 5 is that 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 is greater than or equal to half natural log of 5. P of n here is this statement applied to specific value n. Therefore, when you write P of n, you just write this. Don't write any for all n or like for every n after it. Just write P of n is this statement involving n. So we proved the base case here, the inductive step. The inductive step is an if statement. Assume P of k. Assume P of k. What's P of k? P of k is 1 plus 1/2 plus 1/3 up to 1 over k is greater than or equal to 1/2 natural log k. And we want to show, what is this saying? Where do we want to end up? Where does this proof want to end up at the bottom? And we're saying we want to show, and maybe I won't write this one here. Actually, I'll still write it here. So we want to show, we want to end up with 1 plus a half, 1 plus a half plus a third plus 1 over k plus 1 over k plus 1 is greater than or equal to 1/2 natural log k plus 1. I'm gonna give you maybe a few minutes, maybe 4 or 5 minutes. Try to work this out a little bit yourself, and then it won't be enough time probably to work it out completely, but just to work this out a little bit, and then we'll go over it together. I always use the letter K to signify step, but if you were to sort of side profits, the letter is not so important. It's the assumption that you have in that letter is you want to be able to. We're trying to get it. We're trying to prove it's always greater. Oh, yeah. Feel that. Yeah, exactly. That's step. It's saying use your induction. So basically you can say we know what your K is. You know that some assumption the inductive statement or the inductive step is the fact that when you know this, you get to have
While doing the base case, if we write for example p of 1, and in this case of not this is p as base case, if we write 1 in the brackets, our base case n is that fine or
if n is 1 is the smallest case you have to consider,
and if we write p in brackets 1. Oh no.
I'm also going to erase this board. And then, is it okay if I erase this? Our inductive hypothesis is what we assume. So, well, I mean, I know you might not be finished, but I'm going to go over how to think about going through this problem. So if I look at this place here, this is what I want to show. This is the result that I would want to show. And somehow, because I already know this, I want to use that thing I'm assuming somehow in my brain. But it's probably not too clear exactly where to get from here to here. And so, so what I'm thinking is, I want to use this. Somehow I want to get here. Now, if I want to show this thing is true, I can like in my head I'm thinking I already know this is true. That means if I know this is true, this gives me 1 plus a half plus a third plus 1 over k is greater than plus 1 over k plus 1 is greater than or equal to 1/2 natural log of k plus 1 over k plus 1. What I'm thinking is, I already know this. Let me change this to this, because this looks closer to where I want to end up. So this is something I know. But this isn't quite what I want to show you. Notice here I have the half ln x, ln k plus 1 over k plus 1. Here I only have this. But that tells me if I already know this, I know this is true. Then you can say I actually want to show, what do I actually want to show? I actually want to show 1/2 natural log of k plus 1 over k plus 1 is greater than or equal to 1/2 natural log of k plus 1. I actually want to show this because if I can show this, this is like my new goal. If I can get here, that means I know this is bigger than this is bigger than this, therefore this is bigger than this, which is exactly what I want to show. Now I want to show this. What else can I do? If you look at the problem, there's a fact there that's like ln n plus 1 minus ln of n is less than or equal to 1 over n. Well, let's make this look a lot like that. Because I want to be able to use something that I already know to get here. But, so what I'm going to do is I'm going to rewrite my goal. I'm going to rewrite my goal like this. That's 1/2 ln k plus 1 minus 1/2 ln k plus 1 over k plus 1. Notice this is the same as this. I just moved this over here and flipped them around. This is saying, as long as I can get here, if I can show this, I can get here by just algebra rearrangement. Now, what else do I know? I also know ln k plus 1 minus ln of k is less than or equal to 1 over k. This is something I already know. So this board I look up here, I already know that ln k plus 1 minus ln k is less than or equal to 1 over k. So can I do it? So what do I actually need to know? If I already know ln k plus 1 minus ln k is less than or equal to 1 over k, notice on top, it looks almost like the thing I already know. In fact, if I know that, I also know that 1/2 of it is less than or equal to 1/2 of 1 over k. This is something I know. Because I know the fact on top, I just multiply 1/2. This is something I already know. So now, actually, what do I want to show? I actually only need to show 1/2 times 1 over k is less than or equal to 1 over k plus 1. That's the new goal. Because if I can show this is true, if I can get here, that means I know this is less than this. This thing is less than this. Therefore, this is less than this, which gives you the thing on top. Right? This is the new goal. Now, if I want to get here, what can I do? Well, I can take the reciprocal of both sides. That switches the inequality. So this is saying, as long as I can get here and get up here, well, I can also do algebraic manipulation. I can move k here, k greater than or equal to 1. And I know k is greater than or equal to 1 because the base case is 1. Is this actually the proof? Can I have a thumbs up or thumbs down if I've actually written the proof at this moment? Right, this isn't really yet the proof. This, if you just write this, this is technically a backwards proof. And the reason it's technically a backwards proof is notice where, remember what a proof is. A proof, you start from what you know, and you get to where you want to show. Here, I basically kind of started from where I wanted to, what I wanted to show, and got down to something that I knew. To write this proof formally, you want to write it back up. You want to write it backwards. You want to start here and say, I know k is greater than or equal to 1. Therefore this, therefore this. Once you get here, you can say, I know this from the fact that's provided in the problem. Therefore, so I know this, therefore this, therefore this, so this, therefore this, therefore this. This I know from the fact given in the problem. So that means I know this is less than this, which gives you the last show on the bottom. And you can do some manipulation, you can move stuff around. And then you're saying, well, now I can use the inductive hypothesis. And then you substitute that inductive hypothesis in. And then you can get to what you want to show. So does everybody sort of see how the logic actually flows backwards? But we discovered the logic of the proof like flows bottom up, but we discovered it top down. So one way, so the key takeaway here is that sometimes when you're dealing with induction, you might actually want to start from where you want to end up and backtrack your way back to something that's true, like this. When you are able to backtrack your way to something that's true, then you write the proof by starting from this true statement and sort of like reversing your logic all the way back up. This is a backwards, top down is a backwards proof, but bottom up, if you write this sort of bottom up, you get the actual proof. And now I want to do is, can I have thumbs up, thumbs down on this? Yeah.
Let me just, I mean, from what you're saying, you know, this is like, what should we be presenting on like the test versus homework versus like a publication or something, right? I mean, on a test, do we have to go through the whole thing and then like stop and then rewrite the whole thing upside down?
On the test, if you run out of time, if you get this, and let's say you don't have, I'd say the lowest priority thing, once you get this, sort of the lowest priority thing is to really like spend time rewriting this.
Actually go back and start from
once you get this on the test, if you write this down on the test and you say read it bottom up, that will that's already like that's pretty much good enough. Yeah. If it's like a homework, like if it's a homework and you have like you probably have more time with the homework, and so like honestly the optimal thing is you do actually write it bottom up because it's clearest how the logic goes. But if you actually do run out of time or something and you get this there, you can just say read bottom up. And then
is it not good enough then at the end to say like then it has been shown that this thing must be true, and it kind of points.
I would say okay, in 2000 on the test do say like read bottom up, and like in real life you can actually just write this and this is actually a true story. I was writing a paper and I wrote a proof and I wrote it and I discovered it backwards and I wrote it forwards, and the professor was like, yeah, we don't need to write things forwards, just write it backwards, everyone will know. And but in 2000 it is if you don't say read bottom up, you will lose. I want to go over a second induction problem. I want to go over a second induction problem, which is problem 4 on the practice question. Here, in problem 4, we're trying to show f of n is a Fibonacci sequence is equal to p to the n minus q to the n over square root of 5. And we know the Fibonacci sequence is f0, the zeroth element is 0, f1, the first element is 1, and fn equals fn minus 1, minus 2, where n is greater than 2. I want to show this, and so I want to show this for n greater than this. And and I can say P Q satisfies P squared equals P plus 1, Q squared equals Q plus 1. And the precise values of P and Q are given in the problem. Now, of course, what I'm going to do here, I'm going to start with the base case. I need to show this for n greater than or equal to 0, n equals 0. It's base case f of 0. What's the formula? P of 0 minus q of 0 over square root 5. This is 1 minus 1. This gives me 0. Right? So my inductive step. Oh, I'm sorry. I keep forgetting this. But like, what's P of n? P of n is P of n minus P of n. My inductive step. What do I assume? I assume P of k. Assume P of k. P of k, that's f of k equals P to the k minus Q to the k over square root of 5. And what do I want to show? I want to show f of k plus 1. I want to show P of k plus 1 actually. What's P of k plus 1? F of k plus 1. Square root of 5. A lot of times when you get these kind of, there are a few things here that may really clue you into the fact that you want to use induction. The first is, here's this like, for all natural numbers n greater than or equal to 0.
On your paper, it says n is greater or equal to 2.
For like, are you asking about the base, like why the base case is 0?
Is that straightforward? Oh,
Yeah, so the n greater than or equal to 2 is in regards to this definition, not in regards to but here there are a few things that should really clue you into an inductive proof. Here, this is like for all n greater than or equal to 0, like every natural number is greater, every natural number, that is like the first indication. Here's this kind of formula. That, do you see how the nth value of this Fibonacci sequence is relying on the two things before it? Something, this n is relying on the two things before it. Whenever you have something like that, something is relying on stuff before it, that's a huge clue you want to use induction. So this kind of formula is like indicating induction. Now back to the inductive step. To show this, a lot of times you might want to show. So what I want to warn you about is what I said before about what P of n actually is. P of k plus 1 here is a proposition applied to k plus 1. The proposition is whether or not these two things are equal. This is an algebraic formula representing some number. This f of k plus 1 is also some number. P of k plus 1 is saying, P of k plus 1 is the statement that these two are equal. Notice that P of k plus 1 can only take on values of true and false. It's either true that these are equal or false that these are not equal. And so do not write P of k plus 1 equals this. P of k plus 1 does not equal this. P of k plus 1 is the statement that this equals this. To show something like this is the case, what you usually want to do is you want to start from one side. So start from one side and do manipulations to get to the other. So here, we can start from this side and do manipulations to get here. F of k plus 1. What's f of k plus 1? Well, I'll use its definition. It's f of k plus f of k minus 1. What's f of k? Well, f of k is this. What's f of k minus 1? Just plug in k minus 1. What I can also do now is I'll factor out of p to the k minus 1, p plus 1 plus q to the k minus 1, q plus 1 over square root 5. What is this equal to? This p plus 1. Remember, p plus 1 is equal to p squared. So p to the k minus 1 p squared minus q to the k minus 1 q squared. This gives you p to the k minus 1 is p squared. Add the exponents, you get this. Add the exponents, you get this. And this gives you what you want to show. You got f of k plus 1 equals this.
You only make an assumption regarding what pk is. So why could you use fk minus 1 is blah blah blah.
Right. This isn't totally the right proof. This isn't totally the correct proof. This proof is actually what you might get on a faulty induction. Yeah.
Is there an explanation in regards to base case?
Wait, sorry?
Like what you're gonna explain based on what you wrote on base case.
Yeah, so I'm going to talk about a little bit more about base cases here. So this is actually a faulty induction. And why it's a faulty induction is because of what you mentioned. Here, I relied on the P of K, and I relied on P of K minus 1. So actually, if you trace this proof down, you want to say, oh, P of 0 gets to P of 1. Can you get from P of 0 to P of 1? If I know P of 0, and I try to get to P of 1, this now relies here on like P of negative 1, which was never proved to be true. P of negative 1 doesn't even like exist. So this here isn't totally right yet, because you're still assuming, because here you're relying on two things before, not just one. And so since you're relying on two things before and not just one, you want to now use strong induction. So this is actually strong induction. you want to say something like, assume P of K is true for, let me just make a new variable. Yeah, assume, let's see, P of K prime is true for 0 less than input of K prime less than input of K. Now, by strong induction, now when you have strong induction, now your assumption doesn't just give you the one thing before. It now gives you everything before. Here, when you show P of K plus 1, in the original induction, we only tried to rely on P of K. We realized that that was insufficient. We noticed here that we had to also use the one for K minus 1. We couldn't just use the one before K plus 1. We had to use the two that were before K plus 1. When you realize this in your inductive step, that is your signal to go to strong induction. And notice that when we presented this problem, it's not necessarily clear that you would actually have to do that. Notice it wasn't exactly clear that you have to do that. How we discovered this was we started up the inductive step, noticed that we needed more stuff before, and then that clued us in that now I need strong induction. Now, this proof still isn't complete because I only started with a base case n equals 0. And going down here, if I try n equals 0 up here, I'll still end up with, I'll try to get n equals 1. I'll go down here, but I'll get, if n equals 1 here, remember k is 0. If I try to get n equals 1, here I still get an f of negative 1. I don't want to rely on f of negative 1. F of negative 1 isn't even a real thing. So my P of inductive step can really only start when k is at least 1. Because that means that I can do an f of 1 minus 1 and still get f of 0. But can I now assume this? Here I'm assuming that P of K prime is true for K prime of 0, for K prime equal to 0, for K prime equal to 1, or K prime up to whatever K. This is still like slightly problematic because I don't even know that 1 is true yet. And here I'm already starting up K equals K as greater than or equal to 1. But if I set K is greater than or equal to 1, then I better be able to assume K prime is true for 0 and 1. But I don't know that it's true for 1. So I have to add a new base case here, n equals 1, and say, well, f of 1 is p of 1 minus q of 1 over square root 5. If you calculate that out with the given values, you get this. And so here, the thought process is basically, I was presented with this problem. I noticed that I probably wanted to use induction due to the recursive formula, due to this n greater than or equal to 0. I did the base case. I did the inductive step. Notice that the inductive step, I then noticed that the inductive step relied on more than just the one before. It relied on both before. And having relied on both before, that indicated to me I had to use strong induction. And therefore, I changed the inductive hypothesis to represent strong induction. And then I realized, well, since I have to rely on the ones that are, since I have to rely on the ones that are 2 before, when you have to rely on the ones that are 2 before, you need 2 base cases. That's your clue. When you have K plus 1 is relying on 2 before, first one before, second, and the second one before, that's indicative that you need 2 base cases. Yeah.
How did you know like p to the 1 minus p to the 1 is equal to?
The problem statement gives you the exact values of p. Like p equals 1 plus 5 over 2, q is 1 minus 5 over 2. If you plug in those values. Hurry, can I have thumbs up, thumbs down? I don't want to answer too many questions at the moment so that I can get through everything, and then afterwards we can have a little bit of questions. So after this, so here this concludes sort of our like review of induction, and I want to now go back to doing set theory. And when we're doing set theory, we're going to be able to see very clearly how to use the rules of it. And so I'm going to bring that board back down. and work the set proofs. So we're talking about sets. What are sets? Sets are just like a bag of things. They're a collection of elements. And what's important about these elements? One, they're unordered. And two, they're only concerned with inclusion or non-inclusion. I hope this is not tricky, too tricky, but the point of confusion occurs when it's possible that the elements themselves are sets. So if I have a set that's, let's say, we're going to use the same thing as the bedpost, cat, dog, this graph. I want you to notice that this set A has three elements. The first is cat, the second is dog, the first, the second. Yeah.
Do you mind writing larger?
Okay, I'm sure. And wait, is this okay still? Like, and then I'll write larger in the future, but then like I'll just keep this. And so here in this set, there are three elements. The first, second, third. Really important. I'm not going to go over all the details about like what is what. I believe I unpinned the ed post, but if you would like me to pin it again, I can also pin it again for your review. But I would just emphasize that it's really important that you gain practice in really understanding what is the inherent set and what are the elements of that set, and being careful to realize when certain sets like this are elements of another set. A few definitions. That A union B. A union B is the set of elements. These are elements where X is in A or X is in B. A intersect B. The elements where X is in A and X is in B. A set difference B is the elements where X is in A and X is not in B. A few more definitions. The Cartesian product, A cross B, is a set. This is a set. The elements of those sets are pairs, where the first thing in the pair is an element of A, the second thing in the pair is an element of B. The definition A subset B is that if, you can actually say for all X, if X is in A, then X is in B, and then we have a power set, and that's the set of subsets where S is a subset of A. Notice here, these are also sets. These are subsets of A. Therefore, a subset of A is an, so think about this carefully, a subset of A is an element of the power set. A subset of A is an element of the power set. Is it okay if I erase this part of the board? After these definitions, I now want to do question 5A. Show I want to show this set proof. I want to call your attention to a few things. One is the notion of equality. What it means for two sets to be equal. Let me actually write this here. One more thing. A equals B. X inside A, an element of A, it's an only if. To prove the set equality, we want to actually prove an if and only if statement. To prove an if and only if statement, we have two things we need to prove. The first one and the second one. Notice that it's equivalent to saying whenever you have a set equality proof, you have two problems on your hand. You have part one, the left is a subset of the right, so you want to show left is a subset of the right. Part two is you want to show right is a subset of the left. In this problem, I'm going to do part one, and most likely I'm not going to do part two because I think it's pretty similar. But I'm going to do part one to show that the left is a subset of the right. So I want to show, so part one is I actually want to show this. Now, if we look at the definition, we want to show that for all x, if x is in A, then x is in B. Notice that if-then statement. The if-then statement is this. To show that this is a subset of this, we actually want to show an if-then statement. If x is in here, then x is in here. To show, so this is if x is in this thing, then x is in this thing. Yeah.
Pretty similar to solve.
Yeah. In fact, the if then is exactly the imply. If then and implies are the same. And in order to prove this, what do? I assume the thing after the if, and I get to the thing after the q, after the then. So to do this, I write assume x is in the left-hand side, and I want to get to down here, x is in the right-hand side. Here are two proof strategies that may help you when you work these problems. First strategy, so these two strategies you might want to write down. The first strategy is you want to work forwards and backwards. What this means is you want to work from what you know and sort of work upwards from what you want to show. Remember from the induction, we kind of work this way. When you're doing a set proof, it can help if you sort of go this way and this way. And two is definitions and logic. When I'm presented with this, what am I going to do with this? How do I get from the top to the bottom? And if you get stuck, a lot of times writing out the definition and using that logic stuff will help. Here, if I assume x is inside this, I can just use this definition and write out an equivalent statement that x is inside this and x is not inside C. Now, I'm looking at tip number 1, working forwards and backwards. This is where I want to end up. I can make my goal the definition of this. Because if I can end up at its definition, I'll end up here. So I want to end up x is in this, and x is in this. Notice here, this is the new goal. This is the goal. This is where the goal. Notice the goal is sort of moving up, and here's the stuff that I know. And this is moving down. And we want to get it to squeeze in the middle. Here, what's the goal? Notice the and. To prove an and statement, I prove each of them individually. Therefore, within here, I'm now presented with two subproblems. Part A, part A and part B. The first subproblem is to show this. The second subproblem is to show this. I can now work on each of these subproblems independently. Let's work on part A first. What do? Well, definitions and logic help. So I can write x is in A and x is not in C. This here shows me that I have an and statement. To prove an and statement, I need to prove both of them individually. I need to prove x is in A, and you prove x is not in C. Well, I can prove this easily because I know this. This comes here, and I know this. This means x is in A and x is in B. And remember, to use an and statement, I already know P and I already know Q. So here, this is something I know by definition. That means I know this and I know this. Therefore, I know this. On the other side here, part B, we use something similar. This is my goal. This is the goal. I can rewrite my goal in terms of the definitions. And my goal is an and statement. I need to show x is in B. I need to show x is not in C. This I get from here. This I get because this thing gives me x is in A and x is in B. To use, so this is to prove the and statement. This is to use this and statement. I can use this and I can use this. So I'm going to use this. So I'm going to use this to get here. And so I prove these two individually. I get the and statement. This by definition gives me this. Here, I prove these two things individually. I get the and statement. It gives me this. I prove these two things individually. I get the and statement. this. This is the definition of this. But the other direction is slightly not. The other direction you slightly uses similar techniques. So I'm not going to do the reverse, but I'm going to erase this board on the bottom actually. And so if you need it, feel free to take a picture. Start with B to give you a little bit, to show you a little bit of how to use or statements. B says, so this is now 5B. So here, this to show that again set equality, you show both subsets. You show that the left is a subset of right, right is a subset of left, like this. And so, as before, I'm going to assume X is an element of the left-hand side, and I want to get to X is in. Just one technical detail. It's technically more correct if you say take an arbitrary X in that. And so my preference is that you write that instead of assume X in A union B minus C, but we'll keep it at this for now. And what do? The same. I use these two steps that I did for the other proof. Here we're going to use some definitions and logic. What's the if I know this, it's definition. I want to end up here. I get or. Now this is a little bit tricky because you notice here this is an or statement, and you might come to this table and you say, all right, to prove an or statement is enough to show that one of them is true. If you actually try to do that with this problem, that to show one of them is true, you realize that you actually can't show any of them are true. You actually can't show, you can't just like start here and get down to here, nor can you start here and get down to here. So I just want to remind you that this table is a guideline, but not firm rules. Because in this case, we have an or statement down here, but we can't quite say X has to be in A minus C, nor can we say X has to be in B minus C. Because if you want to like think about it intuitively, if I have my A and C, this first set is A union B taken out C. So we're talking about like this. And then what this is saying is that it's in A minus C or it's in B minus C. But like, I can't actually prove that it's in A minus C. I can't actually prove it's like here. Because it might be the case, nor can I actually prove that it's like in here. So here we notice this or statement doesn't let you just like get away with just proving one. Somehow we're gonna have to deal with this and to get here. And so we're kind of stuck at our goal. We can't do that thing in ands where we split it up or anything. We're kind of stuck here because we actually cannot even prove one of them individually. So we're kind of stuck down here. We can't really move this so far like up and make our goal easier. So let's start at the top instead. I have this and statement. That means I can use but this top part looks promising. This is an and statement. To use an and statement, I can use any of them individually. So what's this? This is x is A or x is B. And I also know that x is not inside C. I can't move up here. What do I do here? What can I do here? I want to probably use this or statement. I probably want to make some use of this or statement. How do I use an or statement? A proof by cases. Use an or statement as a proof by cases. How do I use this or statement here? Let's do a proof by cases. Case 1. The intuitive way of thinking about this is, let's say I know this. That means that I know x is in A or x is in B, but I don't know which one is true. I just know one of them has to be true. Which one is something we don't know. So what we do is we now split into a crossroads and say, in case this is the one that's true, can I get to this conclusion? In case this is the one that's true, can I get to this conclusion? If it's like, in case this one is true, I get here. In case this one is true, I get at the same place. It means that by knowing this, no matter which path I take down this or statement, no matter if it's this one that's true or this one is true, no matter which path I take down, I still end up with the same conclusion. That's what we want to do. Now, here, case 1, x inside A. How can I get down to here? Remember, now this allows us to only prove one. Which one do I want to prove? This one I know x is in A. I probably want to get to prove this one individually. Here I get x is in A. Here I get x is not inside C. Therefore, x is in A, not C by definition. And if I know this, it's enough to prove, remember, it's enough to prove one to get this or statement. This gives me the or statement. Here, x is in B. So I know x is in B. And I know x is not inside C. This, by definition, is this. Here I've proven this one individually, which gives me the full or statement. And so here, notice it's, we took an arbitrary x in the set, we wrote it out in terms of definition, wrote more definitions, we did a proof by cases. We said, what happens if this is the one that's true? This is the one that's true, I get this. Therefore, I get this is if x is in A, if this is the one that's true, I get this. And from this, I get the full or statement. If this is the one that's true, I get this. And so I get this, and so I get the full or statement. This or statement is the definition of this, which is the conclusion I need. Alright, if you guys need this board, go ahead and take pictures. I'm going to move this one up and erase this. Also, does anybody still need this one? Is it okay if I erase it?
Oh yeah.
I want to transition talking about set theory, talking about functions. When we're talking about functions, it's a useful thing to think about bubble diagrams. And when we're talking about functions, you may be familiar with functions being like things like f of x equals x squared, x cubed, or things like that. In this class, we're going to generalize that a little bit and think about functions in terms of bubble diagrams. You want to think about functions sort of doing this. This is a set x, set y. This is called the domain. This is called the codomain. The domain. Another way to think about functions is an input-output system. The domain is the list of all inputs. The codomain is the list of all potential outputs. And let me give an example here. Let me call this 1, 2, 3, 4, 5. A, B, C, D. Let's say 1 is assigned to A, 2 to B, 3, C, 4, 5. Let's put E. Here, the inputs are 1, 2 through 5. Here's the list of potential outputs, not necessarily all possible outputs. And the reason I use potential is because it's possible that some things here won't have any arrows. It's possible that some things here have more than one arrow. Here, the codomain lists all potential outputs, though not necessarily all of them will get arrows, and not necessarily all of them will get just one arrow. Some will get multiple, some may get multiple, some may get none. Why, you might think, why are we going to specify the codomain instead of why didn't we just specify like this? The reason is because a lot of times it's far easier to specify every possible input than it is to specify every possible output. And so let's see if you get a function like x e to the x minus ln x, something like that. You know this thing takes in reals. You know its domain is reals greater than 0. But to say what are exactly the outputs that can come out of this is probably very hard to specify. And so that's why we say this is a function from the reals that are greater than 0 to some real numbers. In other words, this function has to output a real number, but it doesn't. But we're not really saying the exact values it's coming out with. And the reason for that is just because a lot of times it's too hard to be able to specify exactly what those outputs have to be. There are two requirements for a function. The requirements for a function. The first requirement is that it has to be total. That every input is assigned to some output. Second is the uniqueness. Every input has exactly one output. Put this very well, but sort of the main criteria is all summarized right here. Every input every single input has to have exactly one output. In other words, you cannot leave out something. This is not a function. It's not total. Nor can you have some element have two outputs. That's not allowed. That violates uniqueness. When we are talking about functions, there are some special cases now regarding what happens on the right-hand side. Notice that in the definition of a function, we have only restricted the behavior of the left. We have said nothing about the behavior about the right-hand side. We've only said on the left-hand side, every input has to get exactly one arrow coming out of it. And so we have said nothing about the right-hand side. This gives rise to the definitions of injective, surjective, and bijective. Injective we can say for injective, the formal definition is if f of x equals f of y, then x is equal to y. Surjective, for all y in y, there exists x where f of x equals to y. Bijective is injective. Intuitive definitions of these three. Injective means everything in y. So everything, every y has at most one arrow. Surjective, every y has at least one arrow. Bijective, every y has exactly one arrow. This function here is not surjective. The element e does not have at least one arrow. It is not injective. Element c does not have at most one arrow. These are the formal definitions. These inside are the intuitive definitions. All right, I'm going to erase this. If you need it, go ahead and take a photo. I want to do for you an example. Question 8A of the practice questions. Question 8A is proof that that it would be very good if you can be able to do it by heart. It's I don't really encourage memorization, but if you're able to conceptually come up with a proof for 8A, like on command before the exam, that is something that I think that will be a very useful skill that would be indicative of like a good foundation of being able to do these proofs. So problem 8A is something that you really want to be able to do very fluently. 8A says the decomposition of two bijections is a bijection. So we're going to prove, here we have f1, this function f1 going from a set s1 to s2, a function f2 that has arrows going from set s2 to s3, and we want to show that f2 composes f1. This is a function from s1, starts from s1, it goes to f1, it gets to s2, goes to s2, it gets to s3, so s1 and s3 is bijection. So we know this is bijection, and we want to show this is a bijection. How do we show that something is a bijection? We look at the definition, injective and surjective. To prove this, it's the same as proving an and statement. There are two parts. Part 1 is to show f2, f1 is injective. And part 2 is to show that it's surjective. And we'll do the, I'm going to do the injective part first. What does it mean to be injective? It means that here is like for all x and y. Let me change the notation. So there are y1 and y2. Inside y. So for all y1 and y2 inside y, if f of y1 is equal to f of y2, then y1 is equal to y2. To show that it's injective, here, to show that it's, for every y1 and y2, we can say take an arbitrary y1, y2 inside y. And what are we actually proving? An if then statement. Therefore, we're going to assume f of y1. We're going to assume f2 f1 of y1 equals f2 f1 of y2, and we want to end up with y1 is equal to y2. We are proving that this function is injective. Injective is an if statement, so the function in question is f2 f1. So if f2 f1 y1 equals f2 f1 of y2, then y1 is equal to y2. That's why we're to prove that if statement. We're assuming the stuff after the if. We want to get to the stuff after the then. What do we do here now? Recall what we actually know. We want to look for stuff that we haven't used yet, but we still know. We know f1 and f2 are in themselves bijections. So that means f2 is an injection. So if we're looking at this, f2 is an injection. So if f2 of this thing, let me call like smiley face, is equal to f2 of this thing, sad face. F2 is an injection. That means smiley face equals sad face. That means f1 y1 equals f1 by f2 is injected. Now what else do I have here now? Here I'm looking, so I've used this piece of information, f2 is injection. I haven't used f1 as an injection yet. So f1 is a bijection, which means f1 is an injection. We have this. Looking at the definition, f1 is an injection. That means y1 is equal to y2. This by f1 injection. F2, F1 is surjective. What does this mean? This means that for all y inside y for all elements inside the right-hand side, there exists something on the left-hand side, where f of that left-hand side equals to that thing on the right. So what's F2, F1? We can visualize this as like an S1, S2, S3. We've got some arrows here that are F1. Got some arrows here that are F2. F2 composed of F1 means you want to plug in something to F1, then F2. And so to show that this is surjective, we want to say here that let's say every y inside S3 has, let's say, x in S1, or maybe I'll write it this way. For all y in S3, there exists x in S1 such that F2, F1 of x equals to F1. Notice here, this is now, what kind of statement is this? This is a statement about all y. This is a for all statement. To prove a for all statement, we take an arbitrary, in this case, we take an arbitrary y, take arbitrary y in S3, and we want to show here, down here, that there exists this x, where F2, F1 of x equals y. Notice here what I'm doing, I'm taking an arbitrary y, and I'm showing that there really does exist. So here I'm saying, here this is a for all statement, it's for all y, this property holds. So how do I show that? I go up to the table and I say, to prove a for all statement, you take an arbitrary x, in this case, because it's for all y, I take an arbitrary y, and what do I want to end up about this y? I want to end up that this y satisfies this property. So I put this property right here. Now, this is my new goal. I want to show that there exists this x, where F2 of F1 of x equals 1. So how do I prove that there exists? To prove that there exists, I have to give an example. Or more generally, I want to give a procedure for how to generate this x. And show that my procedure actually gives me an x that outputs back this 1. What will be the procedure? Well, let's say this is the y. If you look at these are bijections. Let's say this one is the 1. Well, what's going to map to that y? Well, we're going to have this one thing here. We're going to have this one thing here, and we're going to backtrack to here. How do we formalize this in terms of that? Why do I know that if this is y, I can backtrack 1 into S2? I know that because F2 is surjective. Since F2 is surjective, that means that there is some, not y, let's say there's some x2 where F2 of x2 is what? Because I know F2 is surjective, I know that I'm not, that y isn't going to be, like, have no arrows. Because remember, surjective, every y has at least one arrow. So this y here, I know I'm going to get this one thing back. Now, what about this x2? This x2 is the thing right here. Can I keep backtracking? I can't keep backtracking because I know F1 is surjective. Since F1 is surjective, there exists x1 such that f1 of x1 equals to x2. This is exactly what we have right here. Since I know f1 is surjective, there has to be some x1 where f of that gives me x2. Now, what do I know here? This means that f2 of x2, well, what's x2? x2 is this. f2, so this thing is the same as that. f2 of that equals 1. So what's my example? My example is x1. Here, I show that this value x1 that I've gotten by backtracking is the x1 that you need to get 1. Therefore, for whatever y I do backtracking, I get this x1. And how do I know I can always do backtracking? Because f2 is surjective. Something has to be pointing to this y. f1 is surjective. Something has to be pointing to this. And so you can backtrack all the way to this x1. And this x1 plugged into f2, f1 gives me 1. Therefore, there exists this x where f2, f1 of x is y. What's this x? It's namely this x1 that we got by backtracking. And since I took an arbitrary y and always found some x where f2, f1 of x is equal to 1. Therefore, for every y, there has to exist this x. Every y has to exist this x because I'm telling the reader, give me whatever y you want. My procedure, I'm going to backtrack over. I'm going to get x1. That x1 gives me y. Therefore, whatever y you try to pick me here, I will always find an x1 here that comes back into 1. So this is the proof of 8a. Of 8a. Can I have thumbs up, thumbs down for whether this is very good? I'm going to. I want to do a little bit about countability and relations. Is it okay if I erase this one? The notion of countability is we want to see whether our sets have the same size as the net. And I want so in order to say that something has the same size, to talk about the same size, in finite sets it's pretty easy to say what it means for things that are the same size. But in infinite sets, we have to resort to the notion of functions. And so I think the key thing to remember here is that two sets have the same size if there is a bijection A to B. A set is countably infinite. Countably infinite countably infinite set A means A In other words, a bijection for A to the I believe to say that a set is countable, countable means and this means injection from A to the specific, the very precise definition to I'm not exactly sure whether they changed in notes, so you might want to check that.
Why did you not do that?
Anyway. So the main techniques that I think you would want to worry about is how to prove something is countable and how to prove something is uncountable. To prove something is countable, you want to be able to show that you can to prove something is countable. You want to to prove countable. You want to develop an injection from your set A to the natural. In other words, to prove something is countable, you give an example of an injected function from your set A to the natural numbers. Intuitively, that says there is some way I can count off every element in A, and eventually, when I'm counting them off, I can eventually reach every element. To prove something is uncountable, you have two methods. The first is to show a bijection to another uncountable set. So to show something is uncountable, you can say and another uncountable set. I'll give some examples. Power set of the natural, reals. So maybe you know that the power set. So you know the power set of the naturals are uncountable, and maybe you get some other new sets. And to show that that new set is uncountable, you basically can give a bijection that essentially gives you that like perfect matching between your set and the power set of naturals, or you have a perfect matching between that set and the real numbers, and that shows you that they're uncountable. An example is like if I have this line that goes infinitely in both directions, how do I know that there's an infinite number of points? There's an uncountably infinite number of points on this line. Well, I can basically say like this is 0, and I assign every point a real number. And since there are the same number of, and so every point, I therefore created like a bijection between the points on this line and the real numbers. Since the real numbers are uncountable, therefore the number of points on this line are uncountable. The other technique is diagonalization. I want to do an example of this because it's probably the most confusing. And for that, let's go to question 10A. So 10A, it says to do R and S. I'm just going to do S. So S is a set of infinite sequences of digits 0 to 3. an infinite sequence of digits. S is the set of, maybe I should say this. S is the set, the elements of which are the infinite sequences of digits 0 to 3. So for example, one such element of S, maybe like 0, 0, 0, 1, 1, 1, 3, 3, 2, and so on, and just up to infinity. We're going to show this thing is uncountable. And I'm going to use the technique of diagonalization. Whenever you use diagonalization, you're inherently invoking like proof by contradiction. And this proof by contradiction says, suppose S is countable. This means you have F going from S to naturals injected. I don't know what this function is. I have no idea what this function is, but suppose S is countable. This means that there has to be some function F that is injected. Like this. Notice here we have effectively invoked the rule there for using an exist statement. We know that S is countable. S is countable means there exists this injection from A to the natural. Now, how do I use an exist statement? I give that thing that exists a name. Here, in the table, I gave it the name X, but it can be any name. So here, I gave it the name F. F is that function that is the injected function from S to N, because we suppose S is countable. The technique of diagonalization is a method to destroy any suggested function that you might have. A lot of times when you see a diagonalization proof, you see like a table and you draw the table and you write the diagonalization, that table actually is not really the proof. That table is to demonstrate the technique you are going to use to destroy any possible F. But when you have that table, what I'm going to do is I'm going to say, let's say this F is injected. And then you draw up this table of like this F, saying here's, let me draw it differently. Here's the S, and it goes to a natural. So a lot of times you're going to see this table being drawn. This table here, a lot of times you're going to like fill in some values here and stuff like that and show the technique of diagonalization. That table itself is not the proof, because that table here only takes care of the special case of that table that you drew. Here I'm saying whatever, like this F could be like whatever on earth it could be. I just know this F exists. And I'm going to use the technique of diagonalization to destroy the fact that your F could possibly be the injective function S to F. And this table here is to clarify what that technique is to destroy any suggested function. So here I'm going to show the technique via an example. The example is, let's say you have naturals 0, 1, 2, 3, 4, 5. And let's say 0, let's say 0 gets mapped to like 0, 0, 0. I'm going to write the sequences right to left. But actually, I'll write them left first. 0, 1, 2, 2, 0, 1, 2. Let's say 1, I get 1, 1, 2, 1, 0, 2, 1, dot, dot, dot. 1, 2, 1, 2, 1, 2, 1, 0. Like out of line, but one, 1, 3, 3, 3, 1, 1. So what do I do here? I now look down along this diagonal. And I'm going to make a new sequence here, a forbidden sequence. I'm going to make a new sequence with the rule that if I see a 0, I make it a 1. I see a 1, I make it a 2. 2, I make it a 3, and 3, I make it a 0. But I start looking down this diagonal. Let me just change this. This 0, I'm I'm gonna make a new sequence here. 1. This 1, make a new I'm gonna make this new sequence here. Because I see a 0 here, I make this one 1. Let's see a 1 here, make this 2. You see a 2 here, make this 3. I see a 3 here, make this 0. And so on, and I keep doing that all the way down to infinity. What goes here? It can't go to 0. This thing can't be 0. Because this sequence differs from the one on 0 at this element, at this point in the sequence. It can't be 1 because this thing down here differs from the thing for 1 at this point in the sequence. This thing can't be 2 because it differs from the thing at 2 at this point in the sequence. This sequencer can't be 3 because it differs from 3 at this point in the sequence. You continue that to infinity. This sequence differs from every single one at the corresponding point in the sequence. It differs from the thing for 1 million at like the 1 million and 1 point in the sequence. So therefore, there is no element here. There is no natural number that could possibly be here. Because whatever natural I set here, the way I constructed this is saying this sequence differs from, if I call this n, if this is the natural n, this sequence differs from the nth one at the nth spot. So if this one differs from every n at the nth spot, it can't be any n. There's no possible natural here. But what is f? F is an injective function. Remember, a function requires everything in the input to get something out. This here, this is in S. This is in the input. But this function f doesn't work. It outputs nothing. So this technique of diagonalization is a way to, whatever function you give me, I will generate this new forbidden sequence here. Like a forbidden sequence. I'll generate this new forbidden sequence and show you that your function doesn't work. So suppose S is countable, that means I have some function that is injective. But if you give me that function, I will implement this procedure of diagonalization, generate this forbidden sequence, and show you that your function doesn't work. It maps the sequence to nothing. Therefore, this is a contradiction. Therefore, S uncountable.
You said a table is not proof. Go with a formal.
Well, the formal proof, you would say, like, using the technique of diagonalization, and you say the technique of diagonalization is this technique, and they use the technique of diagonalization on F. And then choosing any kind of arbitrary function. It's saying like any arbitrary function, as long as I use this procedure, I can like kill that suggestion by saying, oh, like this. It can basically kill every single function. Okay, I give my math. What chart? Don't show the chart helps you.
I mean,
It would be a good idea. Alright, so it's 9, you are welcome to go, but I'm going to squeeze in, I don't think there's anybody here after, so I will squeeze in a little bit on relations. I'll squeeze in a little bit on relations, but of course you're welcome to go, and probably only maybe like 10 15 minutes, I'll go over quickly, like the properties of it. Oh, I make this one a one.
Yeah.
I don't really get that.
Okay, so the forbidden sequences, I look at this diagonal. I read a zero. If I read a zero, my forbidden sequence gets a one. Because no better reason than like it works. The rule is this: I see a zero, I put one. I see a one, I put two. I see a two, I put three. I see a three. I just basically what you want is that sequence different from every row by at least one place. So it's different from every row by at least one place. That means it can't be one of the rows in the table. What you just supposed to assign that sequence, that forbidden sequence, some number. But it differs from everything in every row. That's forbidden sequence isn't in the table, but it has to be in the table if you're the function. And so that function is I'm just giving you
That's what you sound like. Anyway, that's not yeah. I like zero it. No, wait, zero? Zero?
You're alright.
So everything goes up.
But why? It doesn't matter what math you do, as long as it's just the one. Your math, your math. So zero math is something that's not one math is something that's not. This will never show up in the table. X plus. It's in a different sequence. Never show up. Never find out. I like this.
I think it's more just like I think you're at
I'm going to spend maybe 10 to 15 minutes to talk quickly about relations. And but I don't think I can get through the question 11 on the practice problems will cover most of the topics of relations. I don't think I can get through the problem, but I'm going to at least cover the general concepts so that you can get it and then go ahead and work on that question. So the relation the relation is really sort of exactly what it sounds like. You're talking about the relationship between two elements of sets. And if I say R is a relation on X and Y, what R is a set. That set is a set of pairs, A, B, where A is in the set X, B is in the set Y. You can almost read this as saying A is related to B. This sentence is intentionally ambiguous. What does it mean to be related to? How you define what it means to be related to is defined by what pairs are in this set. In other words, I can say a relation could be the thing less than or equals to. And let's say I'm doing it on naturals, on X being the natural, Y being the natural. Now, what does it mean for something to be less than something else? Intuitively, we've always said 2 is less than or equal to 3, 3 is less than or equal to 5, 5 is less than or equal to 10, or something like that. But in this statement, notice that a relation is actually a set of pairs, and each of those pairs says that A is related to B. I want you also to be careful. These are ordered pairs. They're not sets. Therefore, the fact that A comes first and B comes second is important. A is related to B is different from B is related to A.
Is the location of relation same as the location for the teacher products?
The same as what? Good question. So is a relation so I think maybe I shouldn't say that R is equal to this. I think this is slightly imprecise. R is a set also of pairs like this. It's a subset of X plus Y. In other words, it's so I shouldn't say R is equal to that. R is in fact a set of pairs. The first A comes from X. The second thing comes from Y. And what pairs are inside the set tell you what it means for A to be related to B. It's whichever pairs you include inside here mean that A is related to B, and whichever pairs you exclude, let's say you have a CD, which is not inside, that means C is not related to D. Is that clear? Thumbs up, thumbs down. So the example is something like less than or equals to. What does it mean to be less than or equal to really on the natural numbers? You can actually call this a list. You can actually make this a set of pairs. What pairs? 0 is less than or equal to 0. 0 is less than or equal to 1. 1 is less than or equal to 0. No. 1 is less than or equal to 1. 0 is less than or equal to 2, and so on. And in a sense, this here gives you the definition for what the less than or equal to means. A is less than or equal to B if that pair AB is inside this set. So I hope you are able to see that the notion of what it means for A to be related to B can be described as a list of pairs of every single pair where the first is related to the second. The less than relation, what does it really mean for A to be less than or equal to B? it means that this pair AB is contained inside the set. The pair 1, 0, we know that 1 is not less than or equal to 0 because the pair 1, 0 is not inside the set. So to talk about what it means for A to be related to B, it is equivalent to talk about whether or not the pair is located inside that set of pairs R. Now, just as we talked about functions, in relations, we sort of have put no restrictions on what things have to be inside the set. We have sort of put no restrictions on what has to be inside the set. All we said is the set has to contain a bunch of pairs, and these pairs, the first thing has to be in the set X, second thing has to be in set Y. No more restrictions. You put another vocabulary thing. If I say R is a relation on X, it means that you have these pairs A, B. This one is in X, and this one is in X. So if there's only one set specified, it just means both of these are from the same set. Now, just as in functions, how we had to describe some special cases of functions, talking about injective, surjective, and bijective, we also have certain special cases of relations that have additional structure or additional properties, and this like additional structure, we have something called reflexive. Symmetric, from here on out, I'm going to basically talk about relations on one set X rather than talking about X and Y. So from here on out, I'm only going to talk about relations on the set X, which means that each thing in the pair are from the same set X. Just to think, one way to think about it, you could say this less than or equal to relation. I can call this a less than or equal to relation on the naturals, because they're both the same. So I'm not going to think about this stuff anymore. When I only talk about relations on the set X. What does it mean for it to be reflexive? For all elements X inside that set X, pair X is something inside the relation. Notice so what this is saying is the, like, for example, is the less than, so this is less than or equal to, this is the less than or equals to relation on the natural. Is this relation reflexive? For any X inside the natural, for any natural number X, little x, is little x inside the relation. So this less than or equal to is reflexive because whatever natural I have, 0, 0, that's inside the relation. 2, 2, that's inside the relation. 4, 4, that's inside the relation. Symmetric. Yeah. X, Y is inside the relation. If X related to Y, then Y is related to X. This is here. Notice that symmetric is not something that you automatically get. Symmetric is a special structure of your relation that you can actually swap the order and you always stay inside the relation. And the reason that has to be special structure is because this is an ordered pair. It's possible that your relation has like 1, 2, but not 2, 1. Is a less than or equal to relation symmetric? And thumbs up and thumbs down. Good. It's not symmetric. 0, 1 is there, but 1, 0 is not. Transitive. If x, y, and y, and x1 is x, y is inside R, and y, z is inside R, then x, z is inside R. Is the less than or equal to relation transitive? It is because if I have 0, 1, and let's say 1, 7. 0, 1, and 1, 7 are both inside R. Is 0, 7 inside? 0, 7 is also inside. Notice here how these statements are formulated. If then, if you want to prove symmetric and transitive, those if-thens should be cluing you in to what we did up there. If you want to prove something is symmetric, you assume x, y is inside the relation, prove y, x is inside of the relation. To prove symmetric, you assume this, prove this. To prove transitive, you assume this, prove this. Does everybody like see the connection between the if then and coming into the relation? And one more definition. One more definition. That's similar to this. Anti-symmetric. If x, y inside the relation and y, x is inside the relation, if both of these pairs are inside, then they have to be the same. Is the less than or equals to relation anti-symmetric? Yes, no. So the less than or equal to relation is anti-symmetric because what this is saying is if x, y is in R. So what does x, y being in R mean? It means x less than y. And what does y, x inside R mean? It means y is less than or equal to x. Then x and y. This is true. Therefore, the less than or equal to relation is anti-symmetric. I want to make sure that you're not confused that R doesn't always mean the less than or equal to relation. R is any relation, any set of these pairs. I'm using the less than or equal to as an example for R, but R can represent any set of pairs. So these four properties are analogous to sort of your injectivity, surjectivity, bijectivity thing in functions. These four properties are properties of relations, whereas the injectivity stuff are properties of functions. This gives you additional restrictions on what your relation, what that set of pairs has to satisfy. Hold this. Now, there are also a few other special structure relations that are in addition to these, and those are equivalence classes. What's an equivalence class? So R, an equivalence class R is a relation that is reflexive, symmetric, partial order is a relation that is reflexive, anti-symmetric. I've omitted the ands in between, but notice that, recall that these actually should be ands. So to prove R, if you have a relation R, to prove it is in fact an equivalence class, you actually have three parts: proving it's reflexive, proving it's symmetric, proving it's transitive. If you want to prove your relation R is a partial order, you also have three parts: prove it's reflexive, prove it's antisymmetric, prove it's transitive. For equivalence, no, not equivalence class. I'm sorry, it should be equivalence relation. So if R, so when you have a relation R, it's possible that R has a special structure and that R is an equivalence relation. How do you know that your relation is an equivalence relation? It satisfies these three properties. Maybe you have a relation and that relation has a special structure that it's a partial order. How do you know that your relation is a partial order? It satisfies these three properties. I think it will probably be best to give a little bit of an example. I think it will probably be best to give a little bit of an example. So this is a very abbreviated version of problem 11. I'm going to start. So 11, you'll actually I'll come up with this set. So as not to be confusing, this is actually the set R plus in problem 11. But so that we're not confused about, so that like things don't get confusing, I'm going to call. Well, let me just do R plus. R plus here is a set. R plus in problem 11, the tricky bit is that R plus is a relation in parts A and B, but then it's the set of things that the relation is acting on in C through G. So so I don't want this to get too confusing, but remember that here we set a relation on set X. Means that you have pairs. The first thing is from X, the second thing is from X. Here, this R plus that I'm going to describe to you, each of them are going to be pairs, but we're actually going to develop relations on top of the set. These elements inside R plus this R plus has the function of X up there. In other words, I'm going to relate pairs. The pairs themselves are not the relation. I'm going to try to relate some pairs. So R plus is a set XY where actually, let me change it a bit. Let me just make XY to be X is in natural Y. And I think this will make things clearer. And also on the practice questions, I'm probably going to change part C through F to represent this set instead. And so instead of calling it, I'm just not even going to call it R plus. I'm just going to call this set X. Or so that it's not confusing, I'll call it X. And after this review session, I'll probably change the question on the practice questions. 11C through F will talk about S instead of R plus. But so let's say we have the set S. And I'm going to want to make a relation on this set S, which means I want to relate pairs, not just relating numbers now. I'm relating pairs. So It's sort of like saying if I have like 1, 1 and 3, 2, how are they related? Are they less than? Like, are they equal? And let's say that I develop a relation. My relation says I'm going to develop a relation less than equal. What's this less than? So I have x0, y0 less than or equal to x1, y1. If x0 is less than or equal to x1, y0 less than or equal to. So what does it mean for these two things to be related? Let's call this thing like smiley face. Call this thing. I don't even know what this is called. But what does it mean for these two things to be related? It means that this one's less than this is less than this. So as long as these two are satisfied, I get smiley face is related to, I don't know, indifferent. But like, so this is the way I'm going to compare the two. This is the way I'm going to compare these pairs. You should be able to verify that this, in fact, is a partial order. It's reflexive because if I did x0 and x0, x0, y0, x0, y0, if I did x0, y0, x0, y0, this is true because this is less than or equal to this is less than or equal to this. It's anti-symmetric and transitive because basically the reason is because the natural number less than or equal to is anti-symmetric. And I'm not going to write it on the board, but I think it's reasonable enough to verify. Now, what's it? So now I want to define maybe an equivalence relation. An equivalence relation is, in a sense, a way of making it so that things are equal. A way of saying that things are equal. A partial order is essentially saying a way of saying things are less than or equal to. This method of defining the special less than or equal to for pairs is a partial order. And notice, and so this is like intuitively you're saying, here's how I'm going to call less than or equal to for pairs. And notice that it basically behaves exactly like a less than or equal to should. An equivalence relation is I'm going to develop a relation, and it's supposed to behave exactly like what equal should. Let's so maybe I'll make my equivalence relation like this. Make my equivalence relation. So I'll make an equivalence relation. X0, Y0 equals, I'll do this, is related to X1, Y1. Related. So if X0, Y0 equals X1, Y1. In other words, this thing that you can also verify that this relation here is actually reflexive, symmetric, and transitive. Keep in mind, if you wanted to talk about the relation on S, you can say this one is R0, this one is R1, and R0, this pair R0, R1 is one of the pairs inside the relation. So, is everybody comfortable like switching between these two notations? Thumbs up or thumbs down. What this is saying is, well, here's what it means. Like, I have all these pairs here. Here's what it means for pairs to be equal. They're equal if the product of the things inside the pairs are the same. I can define other types of equivalence relations. I can say maybe the sum of them are the same, or maybe the difference is the same, or something like that. But here I'm saying the pairs are, two pairs are considered the same if their products are equal. This is an equivalence relation. You can show that it's reflexive because x0, y0, this first pair, this one, R0, and let's say here I have another R0. Are these two related? They're related because the product is equal to this product. I know x0, y0 is related to x1, y1. If I know this, do I know this? I do, because this guarantees this. And if this is true, that means that x1, y1 is equal to x0, y0, which gives me this. And you can show transitive in a pretty similar way. Equivalence relation here is saying, how can I make a relation to describe what it means to be equal? And I'm describing these pairs to be equal if the products are the same. An equivalence class. Let's say I have the element, the pair 112. What's in its equivalence class? The equivalence class is the set of all elements that are equal to this. What's equal to 112? Well, 112 is equal to 112. 2, 6 is equal to 112. 3, 4 is equal to 112. 4, 3 is equal to 112. 6, 2, and 12, 1. The equivalence class of this is the set of everything that's equal to this. A key thing you want to remember, this thing here is not a relation. This thing here is not a relation. It looks like a relation, but remember, our relation is operating on the set of pairs. The relation is not operating on a set of numbers. This doesn't say 1 is related to 12. This pair thing is the object, and we're saying and we're relating pairs to each other. We're not relating the numbers inside the pairs. We're relating pairs to each other. What's the equivalence class of 112? The equivalence class of 112 is every pair that's equal to this. What does it mean to be equals? Well, we define equals to be that the products are the same. So what pairs are equal to 112? It's the pairs whose products are equal to the product here. So it's the pairs which have products equal to 12. Those are the pairs. If you have a you could have a different equivalence. You could even have a different relation. Pull this one. You could actually have a different relation, which is like, let's say we have an equivalence relation. On the naturals. And what it means for them to be the same is that, so what it means for, let's say A equivalent B is that A and B have same remainder divided by 3. So then this, so what is the equivalence class now of 2? The equivalence class of 2 is everything inside. So here, what are we comparing? We're comparing naturals. What does it mean for two naturals to be the same? They're the same if they have the same remainder divided by 3. So what's the equivalence class of 2? We're comparing naturals. So what's the same as 2? Every number that has the same remainder as 2 when divided by 3. Namely 2, 5, 8, 11, 14, so on. All of these things are the same as 2. What does it mean to be the same? They have the same remainder. All of these things are the same as 2. And so since they're the same as 2, and so the equivalence class is the set of objects that you're comparing that are the same as this. So notice up there, that set is not, that set here, don't confuse that with the relation. That set there is all the pairs that are the same as the pair 112. Because up there, we're comparing pairs. Here, the equivalence class of 2 is all the naturals that are the same as 2. What are we comparing? We're comparing naturals. We're not comparing pairs. We're comparing naturals. That's why here we're comparing naturals. The equivalence class has elements which are naturals. Up there, we're comparing pairs. Up there, think about a pair as like one box. And we're comparing pairs. So what does the equivalence class of that pair have? It's a set containing objects which are pairs because we're comparing pairs. Here, we're comparing naturals, and so this equivalence class contains elements which are naturals. One last thing, an order preserving function is, let's say you have an order preserving function is let's say I have a function here, x coming to x. Be sure that let's say I have a function here. Order preserving function is that if x1 is less than x2, or rather x1 is less than x2 if and only if actually, let me write it this way. If set order preserving, what this means is if you have a partial order, call this partial order. If like this x1 is less than or equal to this x2, when you map it over the function, the outputs are also less than or equal to. In other words, let's say that your reals, you have the real numbers, and the real numbers, and you have the function f of x equals x. That is an order, or f of x equals 2x. That's an order preserving function, because if you have two real numbers, x1 is less than x2, then 2x1 is also less than or equal to 2x2. It means that if you have a partial order, if you say like, if I define what it means to be less than or equal to, and in the domain I know that this first element is less than or equal to this second element, that means that when I push it through the function, the output of the first element will also be less than or equal to the output of the second. Notice here, again, the if then statement, to prove that f is in fact order preserving, you want to go up there and remember to assume that you have x1 less than x2 and prove this. If then, to prove this, assume this. So that's basic. I think that basically covers everything except for but there are questions 1 and 2 in the practice. You cover pigeonhole and